Statistical analysis of brain images allows for better understanding of the brain's functionality, detection of abnormalities, and getting insights in such diseases as Alzheimer or Parkinson. How to treat diffusion tensor brain images. How to identify abnormal axonal fibers in the brain. To get insights on these questions, one needs a powerful tool of machine learning. My name is Pavlo Mazharovsky from Telecom Paris, and today I will be speaking about machine learning for anomaly detection and more specifically about the data depth approach. Anomaly detection is a branch of machine learning that comprises methods identifying atypical, outlying, extreme events. Typical examples of abnormalities are defect items in an industrial production process, diseases characterized by atypical inclusions like cancer, financial market defaults, political electoral frauds. In order to detect anomalies, we work with data. Typical data set can be seen as a table of a database where rows or lines correspond to observations, that is, individuals, items, tissue cells, and columns contain their properties. To simplify, think of a set of items possessing only two properties. These we can visualize in a two-dimensional space, for example on a table desk. Given a data set, which may contain anomalies itself, we would like to construct an anomaly detection rule. Applied to new data, this rule will decide which observations are normal and which not. Further, it is even more useful to construct a rule which assigns a score to each new observation, a score which is extraordinarily low for abnormal observations. This fact of having a score for each observation allows us to order them by their degree of abnormality. I will explain now how to construct such a score based on data centrality. This can be achieved via the notion of the data depth. Think of a multivariate data set that is a set of observations possessing finite number of the same properties. Data depth is a function which, for each element of this Euclidean space, measures its degree of centrality with respect to the data. In other words, for each observation, data depth assigns a value between 0 and 1, which characterizes its depth in the data cloud. Observations very central in the data will receive depth values close to 1, while the outlying observations will have depth values vanishing and approaching 0. By this ranking, data depth allows to detect anomalies as observations having low depth values. Let us take a look again at a bivariate dataset. John Tukey defined the data depth of an observation as the smallest portion of the data that can be put into a closed half-space containing this observation. When computing the depth of the red point, we search for a half-space, half-plane in bivariate setting, which contains the smallest portion of the data and the red point itself. This minimal portion will be larger for the points closer to the center of the data cloud and smaller for the points lying far from the majority of the data. Data depth possesses attractive theoretical properties. First of all, it's fully non-parametric and robust. Further, it is invariant with respect to affine transformations. That is, if one transforms the dataset and the point for which the depth is computed in the same affine way, the depth of this point with respect to the dataset doesn't change. Moreover, it gradually decreases on all arrays originating from the deepest point and vanishes towards 0 when the observation goes further from the data. As a function in a multivariate space, data depth defines a family of central regions, which correspond to its upper-level sets. These regions have their characteristics inherited from the properties of the data depth function and describe data with respect to its location, scatter, and shape, and thus can be used as regions containing the normal data. Then, the observations outside this central region are seen as anomalies. Now, consider a more realistic situation, when properties of the observations develop with time or with another functional argument. Numerous examples of such processes include health data of individuals, weather forecasts at certain location, for example, temperature or precipitation, but also those not having time as an argument, for example, frequency, if we speak about spectral data. These data are called time series or functional data to underline that their argument can be different than time. Employing an integration technique, we can use the previously constructed tool, the multivariate data depth, to calculate the functional one. For this, we simply average the univariate depth over all values of the functional argument. The same is true for multivariate functional data, that is for functions which return multiple outputs. Nevertheless, the before seen powerful machinery of functional data depth can be insufficient in certain cases. One of them refers to the data recorded as curves. This can be the case for the roads of people, animals, or transport, neurons or vessels in the human body if we speak about medical data, trackings of natural disasters like hurricanes, handwritten signatures. In this case, parametrizations, that is the way how we record the function with respect to its functional argument, can largely influence and even disturb the results of the statistical analysis. It is even worse if no parameterization is given at all, for example, when we regard the already existing curves. Then, different parameterizations can lead to differing, often not meaningful, and even contradictory results. This can also provide substantially varying ranking of the data, and thus the same observation can be assigned to both abnormal and normal classes at the same time. To capture the curve nature of the data and stay invariant with respect to the parameterization, we modify the Tukey depth. The Tukey curve depth is then defined as an integral over the entire curve of the minimum of the ratio of the portion of data curves to the portion of the curve for which the depth is computed in a half space. When applied, the Tukey curve depth possesses attractive practical properties. It is positive and bounded by 1. It is invariant with respect to shifts and rotations of the data, and it vanishes to 0 if the curve goes further from the data. Among others, a particularly interesting is application of the curve depth in the brain imaging. Here, the depth-based ordering allows to obtain answers on such important questions as curve registration or anomaly detection. It allows to represent axonal paths in the brain, which normally consist of thousands of neurons each, by a single path, the depth median. Moreover, curve depth allows to detect abnormal axonal fibers, those which are either tracing software errors or brain diseases. With data analysis becoming ubiquitous in many scientific fields, data depth is one of its powerful tools. Applied in anomaly detection, already today, it illustrates high potential in getting answers to such important questions as gaining insights in causes of brain diseases, study of natural disasters, analysis of satellite images, and many others.